Israel. Hey, Jay, you went on Jay once. You have any maths today then? Good to see you. Oh, hold on, wait. All right, let me see who here today. All right, Julie coming just now. Jaden here, Siri here, Julie here, Nyla here, Valentina here. Right, and then you guys on that side. All right, folks, morning. Sorry to late as per usual. Now, unfortunately, I can't go past 12 o'clock because I have to go and collect fees from somebody at 12 o'clock and then pick up paper towels. So if you guys had to wash your hands or whatever, you know how to dry them on your clothes or something, right? But I will get some paper towels when I go to collect those fees lunchtime. All right, so guys, today we are working some transformations, right? Okay. Yeah, and something going on with my OneNote clearly because this was happening yesterday too, where the notebooks were deleting, self-deleting. I have no idea why. All right, so let's close that off and reopen it again. Sometimes that happens. All right, so that's not there. It's not there. Is it here? Okay, cool. Right, so let's just rename this to May 19. Rename. Oh, it's the first thing. Look at that. Okay, cool. Okay. All right, so the first one we're tackling today is the May 2019 paper, right? So ideally, morning everybody on YouTube. Yeah, ideally I wanted to spend 4 hours on transformations, 2 before lunch, 2 after lunch, but we kind of cut down to 1.5. So we'll just have to make the best of it, right? After a point, I mean, is end up kind of doing enough, but I mean, can you really ever do enough? Okay, cool. So let's just zoom in here for a little. Everybody have a copy paper? Anybody not have a copy? No? Okay. All right, so it says here, it says May 2019 once again, right? So triangle ABC with vertices 1, 1, 1, 4, and 3, 1. Okay, so you know what? I like to do it. I had to get some slightly different color lines here so we could see these things a little more easily, right? Right, and now let's get some other colors going here as well, right? So sorry, that's the vertex. So the vertex is where 2 of the edges or 2 of the sides meet. So that's A here. So the coordinates here would be, if you go down to the x-axis, that's between 0 and 2, halfway between 0 and 2. Saying YouTube stream not started, really? Sorry, give me 1 second. No, I seen the YouTube stream. There was a false start just now, but I restarted it. So yeah, I've seen it there, and I have some people on YouTube commenting. But in case they hear now. There we go with that. Right, so that's a 1 there. And if you go across to the y-axis, that's also a 1 because it's exactly halfway between 0 and 2. Right? What about the next one, which is B, right? B had coordinates 1, 4, right? So B is there. So if you, B is here. So if you read down to the x, again, you get the exact same x coordinate as A. And if you read across to the y, it's pretty easy to see that the y coordinate is 4, right? And then across here now, right? C is 3, 1. You read down to the x, you get between 2 and 4. So obviously that's 3. And you read across and you get 1 there. Okay, cool. So we confirmed all the different information, the coordinates of the vertices that they give us. What do they want us to do? So ABC is mapped onto LMN by a reflection in the x-axis. So let's highlight that in yellow, shall we? Right? A reflection in the x-axis, and then followed by a reflection in the y-axis. Right. and followed by a reflection in the y-axis. All right, so this is a nice one to start with because it's two relatively simple ones, two reflections. So what we have to do is draw on diagram, draw and label triangle LMN, right? And describe fully a single transformation that maps ABC onto LMN. So the first thing is the item in yellow. We're going to reflect in the x-axis. So when we reflect, now I don't mean sit down with a journal and think about your day and say, well, what did I do right? No, not that kind of reflection, right? Although that's a good reflection to do too. When we are reflecting, think about if you're watching yourself in a mirror, all right? If you watch yourself in a mirror and you raise your left hand, what arm does your image appear to raise? It's right. And if you raise your right, it appears to raise its left. So we call that lateral inversion, right? So sometimes, like when you guys take pictures for social media and you see the words on your t-shirt backwards or whatever, it's the same thing. It's like it's a mirror image. So it doesn't look exactly the same, all right? Your manager, POH pressure, right? Now, the other thing, apart from lateral inversion, is that if you were to put your fingertip on the mirror and stand back on arm's length, right? Your image will appear to do the same. Now, the implication there is that the distance you are from the mirror is the same apparent distance the image is from the mirror as well. Now, of course, when there's an image, there's nothing actually on the next side. Unless, of course, you like to believe in scary stuff. That's a different story, right? Anyhow, right. So, a couple of things. When we are reflecting shapes, images, points in whatever the axis of reflection is, you have to consider those things, right? Let me see if I could put this in a different color, boy. What color would be a good one to put here? Maybe the green? Okay. All right, so what we need to do is for each point, one at a time, we need to make sure, we need to count the perpendicular distance it is from the mirror line. So if we zoom in here, right? Let's take point A. How far is point A via straight line from the mirror line? The mirror line being the x-axis, the one in green. That's just 1 unit. So its reflection would also be 1 unit on the opposite side, right? So that's where, so this point here is where A prime would be, right? We can't call it LMN here because LMN is the final one. What about C? How far is C from the mirror line? That's 1 as well, right? So its reflection would also be 1 on the next side. So that's C prime. What about B? You have to go exactly 1, 2, 3, 4. So its reflection will be 4 perpendicular spaces on the next side, on the opposite side of the axis of reflection. So 1, 2, 3, 4. So B prime is there. So when you close up your shape now, it's going to look like that. So that's the first piece of the reflection, right? Okay. The next thing we have to do is reflect in the y-axis. And let's get a different color for the y-axis, shall we? Let's put that one in orange. So now we have to reflect the blue triangle in the orange line. Okay? The principle of reflection stays the same. Each point will be the same distance away from the mirror line via perpendicular lines as its reflection will be on the opposite side. All right? So let's get a different color going here. I did a green for that. So purple. All right. All right. So point A is how far away from the orange line? 1. So its reflection would be next side there. So we could call that A double prime, but it said LMN, right? So let's use L here. What about B? How far is B from the mirror line? Also 1 unit. So its reflection would also be 1 unit on the next side. What about C? Well, C prime, I should say. 1, 2, 3. So its reflection will be 1, 2, 3 perpendicular units away. All right, and that's N. And all we have to do now is close it up. Okay. All right. So that's how we reflect in the x-axis at first and then the y-axis after that. Okay. So it says on the diagram, draw and label LMN and then describe fully a single transformation. But let's hold it there for a second before we get into the next, right? So of course, I can't just do questions and then you're willing. So then I was saying, who was here this morning? It was Jaziri, right? You're saying you can't just watch the videos. You have to try it. It's like if you watch an exercise video and expect to lose weight. If you do exercise, you can't lose weight, right? So you have to try something, right? So what I want you all to do. So hold on. Before I give you all your assignment, do you have any questions on how I did anything? Or are you okay with it? Okay. So here's what I want you to try for me, right? I want you, right? So let's go back inside of here. What I want you to do now is I want you to do this, but basically 2 reflections again. But here, how I wanted to do it this time, right? So this time, instead of going reflecting in the x and then the y, I wanted to reflect in the y first, right? And then I wanted to reflect in the x after. All right. So again, when you're reflecting 1 point at a time, and you're trying to go perpendicularly until you hit the mirror line. And how many ever units you use to get from your original point to that mirror line, you use the same number of units on the next side. All right. Cool. So this here now. So I want you guys to reflect in the y first and then the x. Any questions? Anybody need a fresh printout to do the second one or? Yeah. All right. Oh, sorry. Actually, no. I'll just pull up Yo. Well, just for the sake of practice, I wanted to do a y and an x, so you know how to do each one, right? But in the actual exam, it says on the diagram draw and label. So I mean, and it's 2 marks. So I guess you get 1 mark for the reflection in the y, and well, 1 mark for the reflection in the x, and 1 mark for the reflection in the y. All right. Not VAPA, it's like visual and performing arts. That's not what it is. I'm not sure myself. All right, sorry. Sorry, what? What? I think so, yeah. It's an installation. Oh shit, that's what. Right, so I went through the question and did what the question asked, right? A reflection in the X, so I reflected in the green line first. Then I went pink to blue, and then from blue to purple, right? So pink to blue is a reflection in the X-axis, and blue to purple is a reflection in the Y. But then what I did after, I gave a separate X. Well, I used the same original pink. I said, okay, instead of doing reflecting the X and then the Y, let's do reflecting Y and then the X. So I'm gonna do that fresh now, right? So you'll basically get the same explanations in a different order. Okay. So once again, let's put that in a thing, right? Right. Right. So when we are reflecting, what do we do? Right? We have to know where the mirror line is. So the mirror line is the orange line here, right? So we have to see how far away each of the vertices, each of the points is from the mirror line via perpendicular travel, right? So long story short, I have to go from A to the mirror line, I have to travel 1 unit to the left, perpendicularly. So the reflected point will be 1 unit on the opposite side of the mirror line. Let's call that A double prime. Same with B. I just have 1 space to shift left, right, perpendicularly to get from B to the mirror line. So therefore, the reflected point will be 1 space on the opposite. Let's call that B double prime. C now, how many spaces are to go? 1, 2, 3. So its reflection will be 1, 2, 3 units on the opposite side. So that's about here. Right? Now, the thing is, you don't actually have to reflect every single one of them using that same method. If you reflect 1 or 2, you could basically use reference to get the reflection. What I mean by that is, look, we know that if we reflect this shape, it's going to look like this, right? And the distance of each vertex from each other will be the same because it's a reflection, right? So if, for example, something was going on with C, we know C, how far is C away from A? 2 units. So if you reflect A, we know we just have to go 2 units to get to C. I'm saying if you reflected A, but somehow you couldn't reflect B, we know that we just go 3 straight units up to get from A to B. So we could do the same thing here as well. Not so? All right, and now we'll close it up. All right, so we just reflected the slightly thicker pink one from the right to the left. So it's a reflection in the y-axis. Sorry, one sec. All right, and now to reflect, actually, no, let me change the color because, all right. Yeah, that's fine. All right, so now we're gonna reflect the blue triangle in the green line. So we use the same exact principles, right? What was the principle, right? When we reflect in each point, we have to count how many spaces it is away from the mirror line. So we're going from A to the green. That's 1 perpendicular space away. So its reflection would also be 1 perpendicular space on the opposite side. So let's call that L. That'll be L, yeah. Right. What about C? Right, that's 1 unit away. So its reflection will be 1 unit away as well. All right, what about B? So again, you could count 1, 2, 3, 4 spaces and then count 4 spaces down. Or you could say, hey, I had to go 3 spaces up from A to get to B. So if I'm reflecting, I have to go 3 spaces down. So M would be here. So let's close it up. Actually, no, I can't use the same color as the guideline. So different color. Okay, let's use the other green, shall we? Is that darker green showing up easily visible? Right. Right, and we happen to end up at the same exact spot. Right, so where they went reflecting X then Y, as in what the actual question asked, or they reflected in Y and X, as what I had you guys practice. You get to the same spot. You get from top right-hand side to bottom left-hand side. Okay, are we okay with the basic principles behind the reflections? Any questions, anybody, anything? All right. Okay, so Let's see if we could answer the other question, shall we? All right. Describe fully a single transformation that maps ABC onto LMN. Okay, so a single transformation maps the pink onto the purple. Uh-huh. Right. So this would be okay. So you could say that it's a reflection in the origin, or you could say it's a 180-degree rotation about the origin. And it wouldn't matter if you go clockwise or anti-clockwise. Now, of course, I know that might mean nothing to some of you all, right? But we'll just copy it down for now. And when we get to rotations, I'll show you, right? Okay. So describe fully the single transformation that maps that onto that. So a 180-degree rotation. Now you could say either about the origin or using the origin as the center of rotation, or with the origin as the center of rotation. And I forgot a very important. Yeah. So normally you would put whether it's clockwise or anti-clockwise before the word rotation, right? But here you can put either clockwise or anti-clockwise, because whether you go 180 degrees clockwise or 180 degrees anti-clockwise, once you rotate about the same center and it's the same shape, you'll get it to the same place. But it only works that way if it's 180. If it's not 180, you can't say that. If it's 90 degrees, you can't say it's either clockwise or anti-clockwise. And I'll show you, right? Yeah, for 360, yeah. And 0 degrees too. But then if it's 0 degrees, you didn't really rotate, you know? Yeah, there's a 360-degree rotation. All right. Super chance. Do you have any transformation videos I could watch? Yeah, this one. All right, Michael, how did I get 180? Right, so Michael, I didn't explain rotations yet. So when I get to it, I'll show you. But for now, we just answer it. Yeah. Actually, I don't. Yeah, you would, because what would happen is if you hold on, let's do our next copy paste, right? All right. So the line you're talking about, so that's actually a good guess, by the way, yeah? Right? So what Nyla is saying is she was saying, okay, maybe it's a reflection line y equal to minus x. Which should come from here, right? All right, so that's the line y equal to minus x. Now, unlike the x and y axis, this is neither a perfectly horizontal nor vertical. 1 second. Hello, good afternoon, morning. Sorry. Oh, you're outside. Okay. Yeah, I'm doing it. Okay, we started a bit late. So I'll give you the question that we just worked, right? Thank you very much. All right, let me just grab that for Julian, and then we'll start. All right. Okay. So Nyla asked an interesting question. What about if it was a reflection in line y equal to minus x, right? Right. So if we apply our principles of reflection, we have to each point, you have to kind of connect each point, draw a line from each point to the axis of reflection, but it has to be like 90 degrees tip, right? So like this one here, you could go 1, 2.5, right? And that looks reasonably perpendicular, right? So on the next side now, you also go 1, and that's a half, then 1, and then 2. So B will end up here, right? Or B prime, or double prime. Now A was only 1 unit away from the axis. So that's A double prime. And then this one is also 2.5. No, this one was 2. All right. Okay. So when you're connected up now, actually is a different color. The blue's blending a little too much. Sorry, give me 1 sec. All right. I know how I get arrowed, but all right. Right. So does that look like what we have down here in green? Nah. Right. It is a reflection, right? But it's not what. It's not a. That would not therefore be the sum of two other reflections, right? So this is a reflection in line y equal to x. Right? But I'm glad they asked that because it gave us a chance to see what a reflection in a diagonal line, how we will go about doing that. All right. But what about the one I said? What about it? I said a reflection in a point. How does that happen? How do we reflect in a point? Now I don't think that's on the syllabus anymore, but just in case, right? So what we would do is check this, right? So what I want to do is if I want to reflect in a point, I want to go from A to here. That's the origin, right? But how do I know how far next I to go? Now this one was kind of easy because it was very close, right? But how we would do it is we would take a combination of horizontal and vertical movement, like vectors, right? So to go from point A to the origin, how many spaces to the left would I have to go? 1. And how many spaces down would I have to go? 1. So now when you reflect, you have to do the same thing on the opposite side. So from that point, you have to go across 1 to the left and down 1. So this point here would be A prime, right? What about B? You'd have to go to the left 1 space, but then down how many? 1, 2, 3, 4. Same thing. You go to the left 1 space and then down 1, 2, 3, 4. So you end up there. What about C? You'd have to go to the left 1, 2, 3 spaces and then down 1. Sorry, I should have shift colors. My bad. I have too many same color blending, right? So 1, 2, 3 to the left and then 1 down. So if you follow 1, 2, 3 and then 1 down, so you end up there. That's C prime. And if we connect everything in a different color now, let's connect. Does that look like what we have here in the green? Yeah, it does. Oh, no? Was it a no? Yeah. Yeah, right. So I have to, that is a reflection on a point, right? Again, I have to double check to see whether that's still on the syllabus because I don't think it is, but it is. It is something that can be done, right? But so when they said in the last piece down here to, wait, where did I already answer? I guess in the first one? Okay. So when they said describe fully a single transformation that maps ABC onto LMN. So it could be that, a rotation with the origin as the center and either clockwise or anti-clockwise, right? Or it's a reflection in the origin. In or through? All right, cool. Now, the next piece they want here is a piece of sketch most of us, right? They want state the 2x2 matrix for the transformation that maps ABC onto LMN. Okay, so to explain that, what I want you guys to do for me, first of all, is I want you all, now they gave us the coordinates of the vertices for A, B, and C already, right? So here's what I want you all to do. I'll start you off, right? So for A, what were the coordinates? Initially it was 1, 1, right? Then for B, sorry, let me use a different color for that one. All right. Let me make sure I have the right. Yeah, that correct. So for B, what was the coordinates? That was 1, 4. And for C, whoops, sorry, hold on, just now. C was what? 3, 1? Okay. So the corresponding point for C is N. What are the coordinates of point N, guys? If you read up to the X, what's that point there? -3. And if you read across to the Y, that's -1. Right? So -3 and -1. So N -3 and -1. So quick question. Do you guys see any similarities between the point for C and the point for N? The coordinates? What are the similarities? The number is basically the same. It's just in one case it's positive, in one case it's negative, right? So this was a +3, this was a -3. This is a +1, that's a -1. Okay. What about 1 and 4? Sorry, what about B? All right. So coordinates for B were here, right? That was 1, 4. And the corresponding point for B is the lowest point down here. What are your coordinates there? -4. Sorry, -1 on the X, my bad. -1 on the X and -4 on the Y. Okay, so for B, your coordinates were -1 and sorry, not B, M, sorry, my bad. Okay, all right. Are you seeing any similarities here? The same, it's the same numbers, just different signs, right? So these were both positive, these were both negative, but they had the same digit, the same number, right? Okay, and what about the last one, which is point A? Right, so A and L correspond. Let's take a look. A had coordinates 1, 1. L had coordinates -1 and then -1. Okay, so when we have a reflection in the Y, sorry, a reflection in the X followed by a reflection in the Y, which is the same as reflecting in Y then X, or rotating rotating 180 degrees about the origin, whether clockwise or anti-clockwise. We want a matrix, but how we want it to look is like this, right? So the coordinates, so let's say, well, I wouldn't use A because A has the same number for X and Y, right? Let's use, sorry. So yeah, let me use C. So it's going to be a 2 by 2 matrix. So we want to multiply to get that. Now, from a very simplistic perspective, what do I have to multiply by 3 to get -3? And what do I have to multiply by 1 to get -1? -1, right? Now, the matrices of transformation for your purposes will all be some variation of the identity matrix. What's the identity matrix, guys? Remember? 1, 0, 0, 1. And the identity matrix is the matrix equivalent of multiplying by 1. Let's say we had 4 and 5 here. You guys remember to multiply matrices? Row by column. So if you multiply the top row by this column here, you multiply corresponding components, or corresponding elements rather. That means you're multiplying the 1 by the 4 and the 0 by the 5. Right? So we have 1 by 4 plus 0 by 5. And then you multiply your second row by the same column. And then multiply the corresponding elements. The first element in the row by the first element in the column. And then the second element in the row by the second element in the column. Okay, let's simplify. What's 1 by 4? That's 4. What's 0 by anything? 0. And then in the second row, 0 by anything is 0. And 1 by 5 is 5. So 4 plus 0 will give us back 4. And 0 plus 5 will give us back 5. Is this not the same as that? Right. So again, 1, 0, 0, 1 is called the identity matrix. Multiplying it by any compatible matrix is like multiplying by 1. It leaves the elements unchanged. Now, quick question. Do we want the elements unchanged here? Or do we want something about them changed? What about them changed? The sign, right? Okay. So would we leave it as 1, 0, 0, 1, or I think we would change something? We have to change something. We'd probably change the sign of the ones, right? In this case, -1, 0, 0, -1. Right? So this matrix here, right, that's the matrix they're asking for. Right? So this is a a 180-degree rotation right? Either clockwise or anti-clockwise about the origin or with the origin as the center of rotation. Oh, good morning, Chris. How are you doing? Yes. True. It comes very often. Yeah. Not necessarily rotations or reflections per se, but something with transformations comes every year. You don't hear anything? Angie? How about now? Yeah, this software keeps throttling my volume down. All right. So how do you get 4, 5? No, I just made that up, Zana. That was just an example. Sorry. Okay. All right. So check this, right? For matrices of transformation, which I'm just going to kind of briefly run through a little bit of it, just I can't do the whole thing, right? For matrices of transformation, this matrix, which is the identity matrix, is like a starting point, right? And we modify either the signs or the positions of the ones, and well, we can't modify the sign of 0 because 0 is neither positive nor negative. Does 0 increase or decrease anything? No, so it can't be positive or negative, right? So what we do is that to get the different matrices of transformation, we have to either switch change the signs of the ones or change their positions with the zeros, right? So let's do another one, right? Actually, hold on. Not that one. Not that. Okay, let's go ahead. All right. So check this. Let's analyze the pink to the blue, right? What we're gonna do, we're gonna analyze the coordinates from the pink to the blue. All right. So the pink had coordinates ABC. Oops, sorry, hold on. That point is way too heavy. Give me a second moment, right? So we have we have A, B, and C. The coordinates of A are still 1 and 1, not so? 1. Right. For B now, still 1 on the X, but 4 on the Y, not so? For C, I had 3 on the X, but 1 on the Y. What about the blue side now? What about the corresponding vertices on the blue side? So this B on top here. Sorry, why is it going to be? What is A? Right? So when after we reflected in the the y-axis as the orange line, right? After, correct. So the the x coordinate is -1, but the y coordinate stay the what? Stay the same. So the x coordinate change, but the y coordinate stay the same. What about B? So B's x coordinate is now also -1, right? But the y coordinate stay the same as 4, right? What about C? C is now -3 but +1, right? Okay. Maybe I shouldn't have drawn one of the grid lines. That might have been a bad idea. All right, so we'll just pull them across, right? Okay. All right, so tell me something. Are these sets of coordinates similar or different? And if so, in what way? Right? So if you went from x, y, what would the corresponding thing be across here? The x would be negative, but the y would be positive. So when you reflect in the y-axis, what changes? The sign of the x coordinate. What stays the same? The sign of the y coordinate. And they also stay in the same relative positions. We don't have any x and y shifting where they were, right? So, if you think about it, right? If we have the 1, 0, 0, 1, right? And you want to get to from xy to minus xy, only one has to change, right? Which one? To go from this to minus xy, which item has to change? The x. The x has to change sign from well, whatever it was to the opposite sign. And we could do so by multiplying by what number? Minus 1. So which of these ones here will have to change to minus 1? First one. So if you multiply minus 1 by x, what do you get? Minus x. And 0 by y will give us what? 0. And minus x plus 0 is minus x. Right? If we do the bottom row, 0 by x is what? 0. 1 by y is what? Y. And 0 plus y is y. So when you reflect in the y-axis, the matrix of transformation is 1, 0, 0, 1. Now, if when you're reflected in the y-axis, the x-axis, the x-coordinates change, but the y stay the same. So when you're reflected in the y-axis, the y-coordinates stay the same, but the x-coordinate change. What do you think would happen when you're reflecting the x-axis? What would change and what would stay the same? Nobody? All right, let's go. That's correct. Yeah, that's correct. Let's go to the diagram. All right, let's take a look at well, let's take out some of these extra little guidelines here, right? They're kind of cluttering up the visual space. The grid lines are already creating havoc. All right, so if you went from this point here to this point down here, right? Isn't it on the same x-coordinate? But instead now of being on the positive side of the y-axis, you're on the negative side. So what would change? The y-coordinate. The x-coordinate would stay the same. What about C and N? When you went from, sorry, yeah. When you went from this point here, down here, you're partially the same point on the x. So the x-coordinate didn't change. But you also went from here on the y to here on the y. So the y-coordinate did change. It changed signs. Right? Sorry. What would happen here is when you're reflecting the y-axis, you go from positive x and positive y to positive x and negative y. What do you think the matrix would be? One, 0, 0 minus 1. When you multiply this row by this column, 1 by x is x, and 1 and 0 by y is 0, not so? And when you multiply 0 by x, you get 0, but minus 1 by y is what? Y. All right, okay. So Anna, that's correct. X is the same value. Correct, very good. Even circle geometry, we did it already, sorry. Right, okay. All right, so let me kind of back off from the matrices for a second, right? So I feel like we were kind of in the zone for like graphs, and all of a sudden matrices appeared. And I feel like people kind of went into like day and headlights situation. Right. Anybody? Nope? Okay, cool. Go. 2 by 2? Why is the thing closed? All right, that's now. Yeah. Hold on, I'm trying to switch it, but they're not letting me. All right, cool. Yeah. Where'd it go? Oh, the 2 by 2? Right. So the 2 by 2 will be minus 1, 0, 0, minus 1. All right. So if you want the signs to change of either one or both of the coordinates, right? You change the signs of the ones. whichever one you want to change. If you want the position to change, you would change the position of the ones. That's the next question. Okay, cool. So what I want to do now is switch to the 2018 question, right? So I'll give you a minute or two to finish copy some stuff down there. Let me just check to see if I have any questions on the side here. Right. All right, ready? Okay, cool. I guess so. All right, so that's, hold on. All right, that's May 2019. Let's do May 2018. Sorry, 2021, my bad. All right, this one's also 2 pages. Give me 1 sec. It was 2, 4, 6, 10 copies. Okay, cool. All right, so while that's printing, let me just insert it. Use. All right, so there's the diagram here. Take a little look-see. GT, can I add you where? All right, so we'll just look at these first 2 things first, right? But let me give you guys your printout. All right, so what we have going on here. So anything in the current section? Which one? From which letter to which letter? against the y, right? A reflection in what line? Which axis? The x-axis, correct. Right? Let's check it out, right? Let's get some colors going for it, right? So all right. All right, so from the pink to the green, that does look like a reflection in the x-axis, right? So that x-axis would be, one second, eh? Okay, maybe that's a little too small. Go a little big on the highlight. Yeah. All right, so that's this line here, right? So how do we just double check that, right? So again, this is just out of curiosity, right? So we had to see, okay, let's take this vertex here. Sorry, let me increase the weight on that point a little bit more. Right, so this vertex here and this vertex here correspond. Right, so what we're going to check for, right, are they the same perpendicular distance away from the mirror line? So from this point here, they go how many spaces down to get it? 2. And if we go 2 spaces, do we get to the corresponding side? But vertex, right? Yeah, we do. All right, so that works for that one there. All right, so this is just some preliminary stuff, right? What about this one here? The corresponding vertex should be across here. So how many spaces we have to go down? Same 2, right? And if you go 2 on the next side, do we get to the next point? Yeah, we do. The corresponding point, rather. And it's sitting here. This top one here, this bottom one here. We have to go 1, 2, 3, 4, and then 1, 2, 3, 4. Right. So this is definitely a reflection in the x-axis. Okay. That Z1 there. That what I look like, boy? A reflection? Probably not. An enlargement? Probably not. A rotation? Does it look like a turn relative to x? Yeah, does it look like a turn, right? Okay. Now, which direction is that? This going this way is which way? Anti-clockwise or clockwise? That's anti-clockwise, right? And now, let me give you a hint. So, usually with these questions, it's either going to be 90, 80, or 270, right? So, check it. If we're going anti-clockwise, right? If I were to connect, so this point here would correspond to which point in the Z? To this point here, right? So check this, right? If I connect the 2 points, let me just give you a hint. So most of the times, the center of rotation would be the origin. So if I join that point to the origin with a straight line, right? And I join that point with a straight line, what angle it looks like it's being formed between those 2 lines there? 90 degrees. Right? Now that's again assuming assuming a lot of things, right? Oh, hey Juliet. Morning, how you doing? Rotation. You mean 90? Right. Right? Now the others aren't as easy to see because those 2 points were exactly on the axis, I should say. All right. So, but before I get a little too right, anti-clockwise. That is Jojo. Very good, Chris. Bro, I'm so cooked for maths. Well, pick a few topics and focus on them. All right. So hold on. What is the question asking us? What's the question? Okay. Triangle X is mapped onto triangle Y by okay. We just said that, right? So what's the mirror line there? Was the axis reflection? The x-axis, right? So let's fill it in one time. Okay. The x-axis. Stay the. Hold on. What is it to stay? Stay the what? The equation. So the x-axis is the mirror line, and the equation of the x-axis. Anybody know? Y is equal to 0. That's the equation of the x-axis. Hey, very good. I hear you. Oh, well, all right. We started late. We did one question. This is the second one. So I'll print it out for you, right? Give me 1 sec. Transformations. How many people every year? Well, maybe you should give him a handout too. I don't know. All right, Nicholas. Right. Okay. So Nicholas asked a good question. Is it always about the origin? So in most of these CSEC participle questions, the answer is yes. Right. However, you can rotate about any point. Right. You could actually pick a point in the shape itself and rotate about that point. Right. Like if I wanted to, like if I pick this point here and I rotated it, right, it would just be like, imagine putting your phone on the table and putting your finger in the middle and spinning it, right? It would spin kind of just around the center. If you put your finger on one of the corners, would the way it spin look the same exact way? No, it wouldn't, right? It would look like it's spinning on a wider thing, right? So the center of rotation will affect the movement, right? Just trying to describe it up in the air is not that great. Okay. Uh-huh. Okay, right. So, yeah, so I was going to do that now. Right. So the question is now, why is the equation of the x-axis y is equal to 0? Okay. Now, let's say we took a different line, right? Let's say we took a line, this line here, right? It's a perfectly horizontal line passing through the y-axis, and it's passing through the point 6 on the y-axis. Now, no matter how far to the left you go or how far to the right, no matter what point, so let's say we pick this point, the x coordinate is what? 2. What would the y coordinate be? 6. If I pick this point here instead, the x coordinate is 3, but the y coordinate is still 6. If I went on this side, the x coordinate is -5, but the y coordinate is still 6, right? So if you have a perfectly horizontal line, it's going to be passing through the y-axis. And as such, the equation would simply be y is equal to, in this case, 6, but it's whatever number on the y-axis it passes through. So if I pass through this point here with a perfectly horizontal line, what would the equation of that line be? Y equal to 4. If I pass through this point here, what would the equation be? Y equal to 1. If I pass through this point here, and again, only with a perfectly horizontal line, right? So what would that be? Y equal to -3. So the x-axis, is it a perfectly horizontal line? Yes, it is. Is it passing through the y-axis? Yes. What is the point on the y-axis through which it passes? 0. And no matter how far to the left you go or how far to the right, what would the y coordinate be of any point? Sorry? The x-axis. Yes, that's this one here, right? So the question was, is it a perfectly horizontal line? Yes. Is it passing through the y-axis? Yes. Through what point on the y-axis is it passing? 0. So no matter how far to the left you go or how far to the right, at every point on that line, right, the corresponding y coordinate will always be 0. Right? Because remember, to find a corresponding y, so let's say we took this point here, right? To find the coordinates, you read down to the x and then across to the y, not so? So the coordinates are -4 and 4. If I took this point here, if I read down to the x, I get -2. Across to the y, I get 6. You with me so? Yeah, like if you pass through here, it's a perfectly horizontal line passing through the y-axis, 3.1. So the equation of that line would indeed be y equal to 1, right? So because the x-axis meets all the criteria, perfectly horizontal, passing through the y-axis, at what point? 0. So the equation therefore is y equal to 0. Right? So always answer the question that is asked of you. Right? Now, if it was a just put it past through the x-axis, you will get a half mark because you're not wrong. It just didn't give them exactly what they asked for, right? Because they wanted the equation of the mirror line. Okay, everybody okay with that one? All right, cool. Aki, so since you sent this, would you? Right, Aki, I'll talk about that just now, right? Okay. Now it says describe fully the transformation which maps x onto z. Okay, so describe fully the transformation which maps x onto z. So we're going from pink. Okay, I didn't give z a color. What color do you want z in, boy? Blue? Mr. Cooper Killer right there. Yeah, I double booked the room. I didn't realize. But only two of Killer students came. The rest of them coming after lunch. So they just joining with us for now. Okay. All right. So we want to go from pink to blue. Sorry, give me one sec. Right. Never Suki. Yep, agreed. Yeah. We're going to go from pink to blue. So earlier, when we just pulled the paper up, we just took a look and said, okay, well, going from here to here looks like a rotation, right? So it's a rotation. Which direction? Clockwise or anti-clockwise? As anti-clockwise. And it looked like a 90-degree angle because we said, look, this point here corresponded to that at the vertices, sorry. Right? So if we assumed, and again, this is an assumption for now, that the origin is the center of rotation, and we connected a line from the vertex to the center there, and the corresponding vertex center there. What angle being formed there between those two blue lines? 90. Right? Now, another way you could tell what angle it passes through without even knowing the center of rotation is pick two corresponding sides. Right? Two sides that kind of match up. So let's say, for example, hold on, let me get a different color here. Crop. Right, okay. Let's say you took this side, the base of the triangle, right? What side in triangles corresponds to that side? This side here. Okay, now check it. Across here in the original shape, that line is perfectly horizontal, correct? It was not your question, guys. Is it horizontal or not? It is, right? And then the corresponding line is perfectly what? Vertical, right? So if you went from perfectly horizontal, right, 0 degrees, to perfectly vertical, what angle you pass through? 90. Right? It's like going from lying down to standing up. Right? Lying down is horizontal, standing up is vertical. So you pass through 90 degrees. Right? So we kind of eyeball that there was a rotation based on the orientation of z to x or x to z. We also said that, okay, if it's a rotation, we're going anti-clockwise. Now you could go clockwise, 1, 2, and then 3. Right? But the shortest path here is to go anti-clockwise. As you want to make it's more intuitive to see it that way. Right? Right. So you have a rotation, a 90-degree anti-clockwise rotation with the center of rotation being the origin. Describe fully the transformation. Okay, right. So that's what we're going to write here. Right. So you wouldn't get the full marks because it's described fully. So a rotation has to travel either clockwise or anti-clockwise. So you have to see it. Now, for us, it could go, even if you have a 90-degree clockwise, that corresponds to another thing anti-clockwise and vice versa, right? So in this case here, right, we could say that, and you also have to see the center. So you have 3 or 4 things. So describe fully the transformation. So it is a rotation, right, anti-clockwise, 90 degrees, and with, now you could say this last part in a couple of different ways. You could say with 0, 0 as the center. 0, 0 being the coordinates of the origin. Oh, that's anti-clockwise. Right? Now, if you wanted this to, if you said clockwise instead, the angle you would use would be 270. It'll be 360 minus the 90 because you're going in the opposite direction. Right. Right. So that's a good question. How do we find the center of rotation? Right. So from 0 to the 20. I think it was minus 20. Right. So it's a 90-degree anti-clockwise or 270 clockwise rotation, and you can say above the origin or with 0, 0 as the center of rotation. All right. Now, let me answer that question then. So somebody asked, how do you find the center? Now, I know you have more parts down here, right? We have 2 more parts, right? But we'll come to that just now. So the question becomes, how do we find the center of rotation? So there's a long way and there's a not so long way. I'm not saying the other way short, I'm just saying not as long. The long way, and the way they would probably want you to do it is as follows, right? What you'd have to do is you'd have to draw a straight line joining the two corresponding points. And then what you'd have to do is find the perpendicular bisector of said line. All right? Actually, I should put that in like a broken line. All right? Right. You have to join with a straight line two corresponding vertices between the original shape and the reflected, the rotated one. So like here and here would correspond, right? So what you would do is, well, and they happen to lie on the same horizon. So you join them with a straight line. And then what you do is you would find the perpendicular bisector. So bisect means to cut in half. Now check this. We could actually do it kind of easy here. I'll tell you why. 1, 2, 3, 4, 5, 6, 7, 8. So if the line is 8 units long, half of it is 4. So when you're bisecting, you'll pass through the 4-unit mark, right? Along the line. Now perpendicular means that at what angle it is? 90 degrees. Do we not have a line passing through the halfway point of that orange line at 90 degrees? The y-axis. Isn't the y-axis already passing through the midpoint at 90 degrees? It is. All right. And where does the y-axis and that broken green line, where do they intersect? At the origin. Right? If you want to triple check to make sure that you have the correct point, what you would do is you join the last pair of vertices. And it also have to find the perpendicular bisector of that line. All right, now that's 1, 2, 3, 4. 1, 2, 3, 4, 5. Hold on. 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4. 1, 2, 1, 2, 3. So here. Right? And then perpendicular will be angle like around this. Right? So yeah, so to find what you call it, the center of rotation, right? What you could do is one, you could guess that is the origin, because most times you'd be right. Or you'd have to do this. You have to join each pair of corresponding vertices with a straight line and then draw the perpendicular bisector of each of them. Right? That's the official way to find the center of rotation. And it has to do with the fact that, all right, when you hear the word rotate, what shape comes to mind? A circle, right? Right. In a circle, we have a line called a radius, right? If you rotate the radius, you basically form the circle, not so? Okay. When you're doing a rotation of a shape, right? Basically what you're doing, so let's say you had this shape here. Right? So this is a random shape in space, right? So what you're doing basically when you're rotating is you're joining the center of rotation. And let's just assume in this case, the center of rotation is the center of the circle. And what you're doing is you're literally rotating, it's like you're joining them with chains or ropes to that center point, and you're literally moving them. But while pulling the ropes tight, because when you do that, what it'll do, it'll send you from that point to somewhere across on the side here. All right. Now I drew it incorrectly because all of the points were supposed to be inside the circle, but that didn't happen. Anyhow, but long story short, yeah, each of those radii, right, would have go back here. Now, the short way that I kind of came up with recently would require the use of one of your implements in your geometry set. And please do tell me you have a fully stocked geometry set for your exam. Okay. Okay. So let me explain my little shortcut, my little hack, right? So you all know in your geometry set, you have some rulers and what they call straight edges, the triangles. All right. So one of the triangles is a right angle triangle, right? Oh, look, I make it know what I'm talking about. Anybody have a geometry set? Have any there? No, not that one. So to have that one, I have our next one. Right, I don't have it there. The next one is an isosceles right angle triangle. All right. Now, oh, you have one? Oh, no. The distance from here to the center of rotation is the same as the distance from here to the center of rotation, right? So if you have a triangle where two sides are equal, what kind of triangle is that? Isosceles. Okay. So the hack I have is that you would I'd have to show you, but it's kind of difficult to describe. You'd have to take that same set square, that triangle, and what you'd have to do is the hypotenuse. You'd have to kind of connect these 2 points with it, and you'd have to kind of shift it around so that these 2 points end up on a actually I can't describe it. I had to show you. I want to say that they end up in such a way that they both end up on the outside of the ruler, the set square, at the same distance from the corner. But yeah, still panicking right now for Friday. I had a panic. All right, okay. Anyhow, sorry. Yeah, I was hoping I could describe my shortcut, but yeah. Long story short, if you get a rotation, best guess is the center, is the origin. If, however, it looks like it's not, then you might have some work to do. But to be honest, they can't expect you to do a set of work for 2 marks or 3 marks. All right, anyhow. Okay, on the diagram, translate triangle Y using vectors -7 and 1. Okay, where's triangle Y? All right. So when they say translate with a vector -7 and 1, what do they mean? Ready? Say again, sorry? Right. So a translation is a shift horizontally and or vertically. So you need a translation vector with a horizontal and a vertical component. Right? Now, either one of them could be 0, but not both, right? Yeah, Lily, sorry. I didn't do that explanation justice. Sorry. Right. Okay. So this is the horizontal shift on the top here. This is the vertical shift below here. Right. Now, horizontally, we could either go to the right or to the left. Not so? If you go to the right, is that positive or negative movement? Positive. And if you go left, is that negative or positive? That's negative. Right? So if they give you a negative horizontal component, which way we had a shift? Left or right? Left. Now, vertically, we can either go up or down. Movement upward is positive. Movement downward is negative. So when you have a positive 1 here, which way are we shifting? Up or down? We're shifting up. Right? So what you would do here for each point is you would shift it 7 spaces to the left and then 1 space up. So like for the point here by the -2, right? We would go 1, 2, 3, 4, 5, 6, 7, and then 1 space up. All right, so let's label these points A, B, and C. Why not, right? So this would be A prime now. Now the truth is, you don't have to shift all of them. You could shift one and just use the relative dimensions of the shape. What do I mean by that? How far is B from the original A? 1, 1, 2, 3, 4, 5, 6. So in the shifting, you're shifting the whole shape. So B will be 1, 2, 3, 4, 5, 6 on that side. So B will be here. All right, and to find C, you have to shift, well, say 1, 2, 3. Yeah, you could count -7 and shift up 1. Or, if you want, you could take it relative to B. To go from B to C, you have to go 2 to the left and down 2, right? So, same thing here. 2 to the left and then down 2. On the sign of the component, that's correct. Huh? Yeah, that one. You want to see it? I've used for a while. Okay. Wait, why am I missing page on Nyla? All right, why not? Orange is a good color. That's not orange, that's pink. Orange? That's orange, okay. A little too close. A green? I do have a green, okay. Let me just see if what I'm saying could work. And then I'll show one person and then I'll let that person show everybody else. Well, each one teach one, right? Okay, what's the next thing they wanted? Just by the way. Enlarge triangle X around center 0, scale factor half. All right, I had to show you that one. Yeah, but when I show you that one, I will break for lunch then, right? Because I had to run St. James to come back. And we have no more paper towels, so I had to get that too. So if you wash your hands, you had to kind of wear them in your clothes. One. Yeah. Got that what? Rant, okay. Oh, okay. There's Vex. Okay. Okay, nah, it didn't work. I thought I had a hack that could have worked to find the center of rotation, but I don't understand why. Isn't this isosceles? That to that, right? That's 1, 2, 3, 4, 1, 2, 3, 4. Therefore, actually it does. It does. Yeah, how to use that. Oh, okay. Okay, that's a little trick. Okay. All right, sorry. Let's do this enlargement real quick, right? Possibility. I'm asking for what? Perpendicular bisector. Yeah. Nah, I've been actually, I gone blank. Don't tell yourself that. Right. So when you're enlarging something, when you hear the word enlargement, what comes to mind? Getting bigger or smaller? Right. The funny part about this is an enlargement that could mean either big or small. What tells us if it's getting bigger or smaller is what we call the scale factor. If your scale factor is bigger than 1, you're going to get bigger. If it's between 1 and 0, you're going to get smaller. Because between 0 and 1, it's only fractions. And fractions are pieces. So here, what's actually happened is we're scaling down. Right? Now, when you scale down, what's going to happen to the shape? It's going to get what? Smaller, right? Let's use our fresh page. Why not? So we're scaling down what? We're scaling X. Okay. All right. Okay. Okay, so when you're scaling down, okay, so first of all, the center of enlargement is here, right? So the first thing you would do is you would join the center of enlargement to each vertex with a straight line. Green. Okay. Okay, so we have 3 lines here. Each of them is from the center of enlargement to the corresponding vertex, right? What we do, right, is we have to basically scale it down. And what that means is that we have to use the scale factor to shrink it, in this case. Now, what do I mean? All right, look, the best way is to show, because I'm trying to figure out a way to describe it, and I feel like I confuse myself. All right, check it. To go from the center to this point here, how many spaces did I need to move horizontally? Any? No, no horizontal. I just went straight up, not so? Right. So that was what? That was how many spaces there? That was 2. So let's say I put the same kind of vector, right? So 0 horizontal and 2 on the vertical. And what I would do is I'd multiply that by the scale factor, which is a half. And when I multiply them, I'm going to multiply by both the horizontal and the vertical. What's a half by 0? 0. What's a half by 2? 1. So what that means is to go, when I scale it down, instead of going 0 horizontally and 2 up, I'm only going to go half that distance. Half of 0 is still 0, not so? And half of 2 is 1. So instead of going 0 and then 2, I'm going to go 0 and 1. So I'm only going to go up one space. I'm only going half the distance. All right? Now, let's check it to the other side. Let's go to the side across here. All right, so what we're going to do, we have to go half that distance. So let's analyze the distance. How many horizontal spaces I moved? 1, 2, 3, 4, 5, 6. How many verticals? 1, 2. So here now, I went 6 horizontally and then 2 vertically. Agreed? So when I multiply by a half, what am I going to get? Right, so 6 by a half will give me 3. 2 by a half will give me 1. So now, when I have to find the position of the corresponding vertex in the reduced shape, I'm going 3 spaces to the left and then 1 space up. That's going to, sorry, let me get a different color. Yeah. So I'm going to go 1, 2, 3 spaces to the right and then 1 space up. So my corresponding point, when I shrink it, is going to be there, by that purple point there. Okay. Huh? Right. And the last vertex is from here. Sorry, it's the last vertex here, right? Let's analyze how we travel from origin to there. So we go how many spaces? 1, 2, 3, 4 horizontally, and then 4 vertically. Right? So we have 4 to get from the center of enlargement to that vertex. So when I multiply by a half to scale it down, what's a half of 4? 2. So now, to get the new position, I have to travel 2 horizontally and 2 vertically from the center. That's going to carry me here. So now, when I connect my points, it's going to look like this. It's going to be a dark purple, huh? All right, so that kind of grape shape there is the enlarged or the reduced version of X. All right, with a scale factor half and a center of enlargement 0. All right. So in the evening, I did, okay, so Zana, from 1 to 3 are doing more transformations because we clearly didn't do enough, right? But 4 to 6 and half, 6 to half 8, we something different. What are you guys feeling after we do transformations? Sure? Stats and probs? All right. Yeah. No problem. Yeah, that's fine. Yeah, and then tomorrow, well, tomorrow is the last day. We all feeling for tomorrow. Well, based on, so measure, oh, we have to do measurement for sure. Okay, Michelle said she couldn't come today, but I told her that they wanted to do tricks. So she said she can't come today and do it tomorrow. All right, but when she come later, we'll confirm, right? Because she's also the mercy of her transport. But push come to shove, if I go and pick up, I can do that, right? Once I have a car. Yeah, guys. So tomorrow, if we do transformations now at 1 o'clock, and then stats and props 4 and 6 o'clock, tomorrow we had to do measurement. What are you all feeling after that? No, the 4 o'clock class and then the 6:30 class, sorry. Huh? We do sequences, and I fill the graphs, right? I fill them graphs. The geometry was an extra thing I put on there. It does. That's the community square graphs. Yeah. All right, guys, we're gonna break for lunch now. After run up St. James. Kayla, you here? Oh. Yeah, that's no problem. So they can mind themselves. I hope. Yeah. All right. So YouTube and TikTok. I had a bounce there, right? I'll see you all later.